Okay. So irradiance, you may also see it written down as intensity. The terms are interchangeable. So the irradiance, girls, of radiation is defined as the energy incident per unit area per unit time. The amount of energy landing on a surface per area of the surface per second, okay, or per time. So irradiance, as I said, or it could be intensity, it is energy divided by area times by time, okay, or divided by time. And we also know that power is energy over time. So we can replace the energy over time part by power, and we end up with an equation of irradiance equals power over time. Okay. So this is always in reference to any kind of light. So it might be a laser, it might be a light bulb. So the irradiance of a light bulb. Oh, so yeah, sorry. What am I talking about? Area, yeah. Thank you. It's Friday. It's the day after a parents' evening. Yeah, power over area. Yeah, so it's, as I said, it's in reference to any light. So it's power of the light source. So it might be a light bulb, it might be a laser. We'll talk about lasers later on, and divided by the area that it's covering. Okay. So I is irradiance in watts per meter squared. P is power in watts, and A is area in meters squared. Okay. So we're going to talk about irradiance in the various different applications. As I said, we will talk about lasers later on. But an understanding of irradiance is relevant to a range of applications. For example, NASA monitors solar irradiance to understand the activity of the sun, and climate scientists study solar irradiance to research the impact of solar activity on the Earth's climate. Interactions between solar radiation and the atmosphere of the Earth can impact on air quality, and understanding of irradiance can allow investigation of the composition of the Earth's atmosphere. Excessive exposure to sunlight has been linked to the development of a range of skin cancers. The performance of solar cells and increasingly common use of solar radiation as an energy source requires an understanding of irradiance too. Okay, so we are going to start with a practical. I know you don't really get the chance to do practicals very often. So we're going to do this practical. You can see I've got it set up on my desk, but I'll also show you a sort of bigger picture of it there. So I just took this photo this morning and I've labelled it. Okay, so what we have is method that I'm giving you is filled with errors. Okay, and there's a reason that I'm giving you it with filled with errors, because I want you to think about how you could improve this experiment in the future. Okay, so light bulb. We've also got a phototransistor here. This little black thing here is a phototransistor. Okay, so phototransistor, if you remember about when you did semiconductors, you might not remember. It's basically when light falls onto it, it basically sends a signal. Okay, so and it's connected to a voltmeter. So that voltage reading on that voltmeter is directly proportional to the amount of light that's landing on that phototransistor. So it's basically a light sensor. Okay, but we read it in units of volts because we're connecting it to a voltmeter. Okay. So what we do with this phototransistor is we're going to start it probably about 20 centimeters away, and then we're going to move it back, and we're going to record the amount of light in volts, because it's just measured in voltage. It's still a measure of the amount of light at various points further away from the bulb. So we're moving it further and further back, measuring how much light there is. Now, just to point out, when you're using these phototransistors, inside is a battery. Okay, what you have to do is you have to connect the battery before you can use it. So you basically just have to sort of plug it in. Okay, you'll see what you see. You just need to pop the lid on the battery kind of thing so it's connected. Okay, and then the actual sensor is a little circle on there. You'll see it. Okay. So you're going to do that experiment. So if we go back to our note, so we're going to investigate the relationship between the intensity, I, of light. See, it's already been called intensity instead of irradiance. They're both the same thing. And the distance from a point source of light. Okay. So there's our lamp, distance away, and a phototransistor. So what we're going to do, as I said, we're going to move that phototransistor, start off at about 20 centimeters and move it further and further back in equal increments, which will just help you when you're plotting a graph, and measure the light intensity in volts. Okay. So, but the first thing that you need to do before you do anything like that is measure the background light intensity. Okay. What is the light intensity when there's no light bulb on? So the light intensity in the room. I will turn the lights off when we do this experiment so you can measure the background light intensity. Obviously, it's not going to be ideal in here because we don't have blackout blinds. We can close the blinds as far as we can, but there are gaps in between them, things like that. Okay. So you're going to do distance between source and detectors. As I said, the reason that I started at about 20 is because if you get too close, if the light's too bright, sometimes it messes with the phototransistor. So 20 centimeters is usually a good place to start. You can go up in tens if you want to. If you want to go up in five, you can do. Completely up to you. And then you're going to measure the voltage on the voltmeter. Then there's two of the columns here. One, I want you to work out what d squared is. And then this one, 1 over d squared. Because once you've done that, you're going to plot 1 over d squared versus your voltage, your radiance. Okay. Right. Any questions? So all of the equipment should be around the room. I'll move actually some away from Becca, so there's equipment over here. And then you can just